All right, next one. Grocery store receipts show how much a customer purchased during their visit to the store. In summary of grocery store receipts over the past 5 years. It has been found that the receipt values follow a positively skewed distribution with mean and standard deviation. Now, the mean part tells us it's quantitative. The mean part tells us that we need to do the central limit theorem. But the positively skewed distribution, what do we think there? That's not a normal distribution, so sample size has to be bigger than 30. So what is the probability that A randomly selected? Guys, this implies n equal 1. No can do. Sample size isn't big enough. And I don't know how many times I will see students and they'll pick up that calculator and I'll say, no, you can't work that problem. And they'll be like, oh, yes, I can. I can do this. And I can go to normal CDF greater than 100. I can go up to E99. I can put in the mean of 72. And I can put in the standard deviation of 32. See, I told you I can work that problem. Well, no, you can't. Because, guys, we have a positively skewed distribution, not a normal distribution. So if this said positively skewed CDF, I'm with you. But you're not going to find that calculator key because it doesn't exist. You're assuming you have a normal distribution when you work this, this problem this way. Guys, we don't have that luxury. We don't have a positive or a normal distribution. We have a positively skewed distribution, and we need sample size 30 or bigger. What's the probability that n equal 28? Well, that's close, isn't it? But it's still, guys, there's something magical about 30. You could get a pretty good approximation because this is close to 30, but it wouldn't be close enough. All right, gang, last one. What's the probability 75 randomly selected customers spends an average of more than 100? Well, we've got everything set up that we need, don't we? The only thing we need to do is come in and divide by the square root of the number of customers, which is 75. Average of 100 or more. And now, it is so tempting here, I see students do this a lot, to report this as 1.77. Guys, probabilities are between 0 and 1. And, 1.77 obviously hidden. So always look for the scientific notation which says that we need to move this decimal place 14 places to the left. So essentially you put in 13 zeros and a 1/8. Now, I don't know about you, but that got a little silly with all those zeros. So, guys, what I would, how I would have written this is just approximately 0. Once it gets to a point, I don't think there's really any standard on it, but once it gets to a point where you get sick of drawing zeros, I just say approximately 0. All right, number 3, in your own words, describe the difference between x bar, mu sub x bar. Guys, this is the sample mean. This is the population mean. And this is the mean of the distribution of sample means. Sample mean, population mean, the mean of the distribution of sample means. Sx, standard deviation for the sample. Sigma, standard deviation for the population. Sigma sub x bar, well, standard error, but it's the standard deviation of the distribution of sample means. So the mean of the distribution of sample means, the standard deviation of the distribution of sample means. All right, gang. Some business analysts estimate the length of time people work at a job has a mean of 6.2 and a standard deviation 4.5. If n equal 150 people are selected at random, what are the mean and standard deviation of the distribution of sample means? Well, guys, the mean of the distribution of sample means is mu sub x bar, which is just the mean of the population, which is 6.2. And the standard deviation of the distribution of sample means, so this is 4.5 over the square root of 150. So guys, put that in your calculator. And I get 0.3674. Guys, this is really going to play an important role here in the next week or so when we start into inference and we start looking at confidence intervals and test statistics and things like that. All right, gang, let's switch gears. Central limit theorem proportions. I wish I hadn't put that up there because that kind of takes away the punchline. But results from a Gallup poll indicate that 6%. Guys, what should you think here? Categorical. 6%, 0.06, 6 out of 100. Regardless, again, remember, we can express this as a fraction, as a decimal, or as a percentage. Those are all equivalent. This is the way it's usually expressed. This is the form we usually work with. So a random sample of 300 adults is selected. What is the probability that 20 or more has bet on college sports? First thing I need to do is I need to calculate my p hat. So my p hat is my count over my whole. So we're focusing on 20 out of 300 or more. So I'm going to make that so I'm going to go with 0.067 as my p hat. Now, central limit theorem tells us that if n times p, n is 300, p is 0.06, so 300 times 0.06 is 18. And if n times 1 minus p, well, n is 300, and 1 minus p, 1 minus 0.06 is 0.94, which I don't even need to look at that. That's definitely bigger than 10. And again, guys, where's where's all this coming from? Remember back here, we got conditions. We don't have sample size restrictions of 2 and 30. We have this n times p and this n times 1 minus p. Both of those have to be greater than 10. And when I check the conditions here, I see that this is 18, bigger than 10, and this one's clearly going to be much bigger than 10. What this tells me now is that I can use normal CDF to work my problem. This tells me that the sampling distribution will be normal. So therefore, I can use normal CDF. So I want the probability that 20 or more out of these 300 with a mean of 0.06 and a standard deviation of 0.06 times 0.94 divided by 300. Now, where's that 0.94 come from? Well, that's 1 minus 0.06 0.06. All right? Guys, these are a little harder. What makes these harder is the notation's tougher. So, gang, what I can do, I'm going to go to this graphing calculator. So, second function distribution, normal distribution. So, my lower bound is 20 out of 30. I'm sorry, 20 out of 300. Shoot. 20 divided by 300. I want or more, so I'll go all the way up to E99. My mean is 0.06. My standard deviation is the square root of 0.06 times 0.94 divided by my sample size, which is 300. Paste it, hit enter, and I get a value of 0.3134. Let me go back and check that. I saw a parentheses that was kind of out of whack there. Maybe I didn't. Okay, no, I don't guess I did. No. All right, gang. What if you've got the other type of calculator? Let me show you how to work it too. If you got the other type of calculator, you just put things more directly. So you still go to normal CDF. Again, as long as the n times p and n times 1 minus p are bigger than 10. So here we need 20 out of 300. We need to run that all the way up to E99. We need the mean of 0.06. And we need a standard deviation of 0.06 times 0.94 divided by 300. And you'll see we get the same number. It's critical here, again, that on this standard error that you realize that everything has to go under the square root sign. So don't close that percentage or that parentheses too soon. If you do, you're just going to get the wrong answer if you do. Okay, when n equals 200, that's a hard problem here, but we can do it, okay? So, when n equals 200 adults, what sample proportion represents the 60th percentile? Well, guys, we know that from the central limit theorem, because n times p and n times 1 minus p, now when it's 200 times 0.06 would be 12, bigger than 10, and this one's clearly going to be bigger than 10. So we know when n times p and n times 1 minus p are bigger than 10, that we'll have a normal distribution centered at the percentage we start out with. All right? Well, there has to be some p hat right there that has 60% of the sample proportions below it. Well, guys, from previous problems, how do we find a score from a distribution that has a given characteristic? We use inverse norm. Guys, I'm not sure what happened here. What's going on? All right, whatever. So, guys, inverse norm requires three things, doesn't it? Inverse norm requires us to put percent below the decimal, the mean of the distribution, and the standard deviation of the distribution. The mean and the standard deviation just turn out to be different. So guys, the correct answer is 0.0643. Now, if you're on a test and you'd like to examine that to see if it's realistic, well, I mean, let's test it out. What we would want is the area under the curve to the left. So this is going to be from negative V99 to 0.0643. With a mean of 0.06. You guys, sample size wasn't 300, it was 200. Now, if we got this right, we should get an answer awfully close to 0.60, and you know, that's close enough for comfort for me. And it's 0.62, but you know, we're off just a little bit, but not nothing too crazy. All right, so I would feel pretty comfortable with that. All right, gang. Next problem. Stuff set up here. A random sample of 150 adults is selected, and 10 admit that they have bet on sports within the past 12 months. Find and interpret the z-score. All right, guys, this is going to be pretty important. As if your life wasn't tough enough before, this is going to be your see all, do all, know all about z-scores. From here on out, you're going to have 3 types of z-scores that you're going to have to be responsible for. The first 2 deal with quantitative data. And one deals when we take a sample size out of one randomly selected observation, and we let that value be given as X. And the z-score in this situation is just take that score minus the mean divided by the standard deviation. That is the z-score. The other situation is if we have n greater than or equal to 2. Everybody's probably grabbing for their phone, right? Anyway, sorry about that. So if n is greater than or equal to 2, we don't look at a... hold on. All right, let me see. I'll tell you what, let me send this text real quickly. All right, so if we have sample size 2 or bigger, let's say we have 5. Well, we take those 5 scores, divide by 5, and we get the mean for those 5 scores. In this situation, our focus is on X bar. We still subtract that from the mean, but we divide by the standard error instead of the standard deviation. Now, guys, I always put these in parentheses because you know, to put this in your calculator correctly, it must be put in parentheses. I got to tell you, my wife is kind of redesigning our bedrooms. Our house we live in, our house we own, we just don't live in it. Has 3 bedrooms, so we're painting all of it and stuff. So she's at Lowe's and she's driving me insane. I did not say that. All right, categorical variable. What do we have here? Well, in these types of situations, let's think about what we have for every z-score. Essentially, for every single z-score that you will ever run into in your entire life, you have three parts. Up here it was x, this was the mean, standard deviation. The score, the mean, the standard deviation. What does this and this represent? What we get from our sample. In these types of problems, what do we get from our sample? Our sample proportion. Mu and mu are the population mean. The population mean in these types of problems is just p. In the denominator is the standard deviation. Standard deviation, we call this the standard error. So it should make sense that the standard error goes right there. Now guys, let me point something out from having taught this class a zillion times. Students often get, this standard error. And I see this happen all the time, and I don't know why you guys do that. Well, not you guys, but previously. I tell you without question, I speak it through and I tell you that n goes under the square root. But inevitably, students, and I see it all the time, will write it like this. This is not the same as that. Put it in your calculator for some p and n. It doesn't give you the same answer. This is not what you want. It's this one right here. Now, if you wake up tomorrow and you think, you know what, I just like to do statistics wrong today. I like to get all the wrong answers. Then do this right here. You'll achieve your goal. You will never, ever, ever get one of these problems right if you use this as a standard error. That n has to be under the square root. It can't be in the denominator without the square root. So again, I just point that out because I see that happen an awful lot. So guys, the z-score for sample proportions is p hat minus p over the square root of p times 1 minus p over n. All right, gang, let's make it happen. This problem right here, what's my p hat? What's my count out of the total? So 10 divided by 150 is 0.066. I'm going to go out quite a bit for more accuracy. So now what I can do is I can find my z-score to be and I'm going to show you a way to do this in your calculator that makes it much easier, okay? So 0.0667, what was the mean? Well, that's the percentage we start with in these problems. And the standard error is going to be 0.06 times 0.94 over the sample size, which is 150. Now, guys, this is worth the price of admission right here. I'm going to show you how to do your calculator where we don't have to round that off, okay? So I just do this. I do the 10 divided by 150, so I have it stored in my calculator. What I can now do is I can go left parentheses, and you'll see right here where I'm pointing ANS. This ANS command will bring the answer from the previous problem and insert it into the problem that we're working, the expression that we're trying to find the value for. So if I go second function answer, it's going to bring that 0.066666 repeated decimal forever, where if we round it off, we get an approximated answer. So we're going to get a better answer this way. So 0.06 and we want to divide by the square root of 0.06 times 0.94 divided by 150 and close it up. So guys, the z-score is 0.34. So I found it, but now I need to interpret it. So I would say that a sample proportion of 10 out of 150 is 0.34 standard errors above the mean. So again, a sample proportion of 10 out of 150 is 0.34 standard errors above the mean. All right, what sample size will result in a standard error of 1.75%? Well, guys, the first thing you've got to realize is never do math with a percentage. If you do math with a percentage, you're going to look stupid. If you go down and invest $1,000 at your local bank and they tell you they're going to give you 2%, and you do math with a percentage, and you go down there a year later and you're saying, okay, give me my check for $2,000 interest, you're going to look stupid because you can't do math with a percentage. You've got to do math with the decimal. And then you go down there and you get your 20 bucks. You're not as happy because it's not as much money, but at least you don't look crazy. Guys, you can't do math with a percentage. So the first thing I got to do with this 1.75, I got to change it to a percentage by moving the decimal place 2 places to the left. Okay? Now, I want my standard error which is the square root of p times 1 minus p over n. Now guys, this is going to be one of those things you're going to remember for your midterm because there aren't questions like this on Hawks, but there are going to be questions like this on your midterm. So, all right, so let's put stuff in where we want. We want our standard error to be 0.0175, and we want to find the sample size that gives this. So again, where's that 0.94 come from? This is 1 minus 0.06. Guys, let's square both sides. So over here I get 0.0175 squared. And on this side I get 0.06 times 0.94 over n. Now, guys, I'm going to show you a trick that helps a lot in statistics. Now, I'll come back to this in just a second. There's a trick in statistics that says if you have a fraction equal a fraction, so we all have to agree that 1/2 is the same thing as 5/10. This property says that these numbers on the diagonal, we can interchange those and we don't violate the equality. So I can take that 10 and put it up here. And I can take that 1 and put it down here. And 10 over 2 is still 5 over 1. I can also change these values. So 1 over 5 is the same thing as 2 over 10. I can take things on the diagonal as long as it's equal to. I can take things on the diagonal and change their position from one diagonal to the one part of the diagonal to the next. Now I can't do that if I'm multiplying. I can only do it if I have equal sign. Well, guys, that turns out to be really, really, really handy in this situation because if you'll allow yourself to think about that being over 1, we have a fraction equal a fraction. And what it tells me is I can take what's in the upper left-hand side and what's in the bottom right-hand side, and I can change those. I can put the n up here, over 1, but that's redundant. And I can put the 0.0175 squared, where the n is, which minimizes the steps required to work this problem. And if you can minimize the steps that are required to work the problem, it's my experience in teaching, as long as I have, that you got a better chance of getting the problem right. So I need 0.06 times 0.94. Divided by 0.0175 squared. And guys, sample sizes, you always round up. This right here, if you were to round appropriately, this would go to 184 because this 0.1 is less than 0.5. Typically, if this is 0.5, we'd round it up to 184. If it's less than 0.5, we keep it at 184. Throw all the typical rounding rules out the window. When you're solving for n, always round up. So guys, our sample size here would be 185. So we would need a sample size of 185 to get a standard error of 0.0175 or 1.75%. All right, gang, this has been a long video. But I'm done.